today we are going to be discussing optimization and uncertainty quantification in partial differential equations. So this is a really big topic, so I'm only going to be scratching the surface. And in particular, I'm going to introduce just one particular type of method, the adjoint-based method. And nowadays, deep learning is very hot, and like underlies all the deep learning stuff is a technology called backpropagation. So we'll also be talking about this today. It's just a special case of the adjoint method we are talking about. And the training a deep neural network is just solving an optimization problem. So optimization problem in the context of a partial differential equation can usually be written as minimize over a parameter space. Let's say S in a parameter space. Let's write it as big S. A function J that is written as a function of two things. One is, of course, the parameter, but the other is a solution to a differential equation, right? Okay, and U is the solution to a differential equation, and basically, I usually write this as a constraint such that this G, a differential equation or algebraic equation, if you're doing machine learning. Okay, so minimize J subject to G of U and S is equal to 0. So this can be a PDE, it can be some PDE plus other constraints. So basically we are going to be discussing how to solve problems like that. And uncertainty quantification, so this is optimization. Uncertainty quantification is a little bit different, but like it's similar in that I want to characterize the distribution of the objective function, let's say J U of S, okay, and given the distribution of S, and that U satisfies the differential equation. Right, so for optimization, S can be, for example, the geometry of an airplane. I want to optimize the geometry of the airplane such that the drag, which is not only a function of the geometry, but also a function of the flow field around it, is minimized. And the geometry controls the flow field via an implicit relationship. That is the differential equation we are going to be solving, right? So U is the flow field. G is the differential equation that relates the flow field to the geometry, and S is the geometry. J, if you can pose the same problem in terms of a uncertainty quantification problem, so S again can be the geometry. And I know when I'm making an airplane or a part of an airplane, I'm not going to be making it to exact precision, right? There is manufacturing variations. So if I can measure from a particular manufacturing process what are the expected variation, then I want to quantify what is the distribution of lift, or let's say what is the distribution of range or some other important quantity. You want to make sure with like 99.9% probability it satisfies my design criteria, right? Yeah, similar problem can be posed in many other fields. So today we're going to be discussing a particular way of doing this in the context of very large problems.